We were in the process of discussing beam hardening. Before we were required to start all over again because of the 40-minute imposition. So beam hardening, as photon beam traverses matter, the effective energy increases. How does this happen? A layman might not make out any sense from it. You have something going through, let's say a vehicle colliding with be involved in an accident. At the end of the day, you should come to rest. At least the kinetic energy should be reducing. But this is not the case with photon. It's X-ray and the photon and the gamma ray. As they traverse matter, their effective energy increase. How? Because I don't want to go into the pieces of that, the mathematical operation. But what I have to say here is we have particular, okay, we have three attenuators. So we have three attenuators or three HDLs. We have calculated the HDL of this particular beam and then found it to be this particular value, maybe 2 millimeter of aluminum. And again, lest I forget, the HDL is usually given in terms of maybe millimeter of aluminum, millimeter, and you see something millimeter of aluminum. When you see this, you're talking about an HDL. You can see millimeter of copper, millimeter of lead, so on and so forth. Talking about the attenuators and thickness. So we have let's say 2 millimeter of aluminum, 2 millimeter of aluminum, 2 millimeter of aluminum. We have a polyenergetic beam passing, and you have so many of them. Ones that can have higher energy, intermediate energy. In fact, so many energies. Let me say 4 energies. Encounters this. At the end of the day, you might have just the more energetic ones passing through. And then here, let's say 3. Here you have 2. Remaining here, at the end of the day, you have this is what happens. You have so many energies here. And they pass through. This one will remove the ones with a lesser energy. After that is what we use in filtering whatever the X-ray machine. And they have so many components and filtered it. So this can be seen as a filtering. This one will remove the lower energetic one, because the lower energetic photons will have enough energy to penetrate, to pass through. They will be absorbed via their excitation and then excitation and so on and so forth. Few will move out. Like I said, they encounter another one. This one will have the ability to reduce and further reduce, remove the low energetic ones, and so on and so forth. So then you have just highly energetic, this one has solar energies, 80, 70, 60, 55, and so on and so forth. So this one I remove 55 and 60. I don't even add the 90. So that the 90, 80, 70 will go through. This one will just give us around maybe 70, maybe 85, and the 90 passing through. At the end of the day, just have mainly 90 keV of photon passing through. And see, at the end of the day, you have, if you calculate the mean energy of this one, you're going to have something close to 80 something, maybe 87 mean energy. For mean energy of this one, I'll be looking at something like 3. Mean energy of this one might give us something like 65. You see, the energy continues, the effective energy. Of course, in this time, we're looking at the effective energy. We're not just looking at energy, because we have so many energy composition. So you see, energy continues to increase. This is because it is a polyenergetic beam. Polyenergetic. If it had been a monoenergetic beam, we wouldn't have this. We wouldn't have this because we are talking about just one energy. For 3 second beam, we won't have one energy. I think we are talking about a monoenergetic beam. If you have 40 photons here, 40 photons, this one is going to remove exactly 40. So I mean half, which is 20. So I'm going to remove exactly half, which is 10. This one is going to do exactly half, which is remaining 5. In this one, of course, the number that will be removed is also there. But because it has so much energy, various energy, this one we just focus on the number of photons. So at the end of the day, 20 over 40, 20 over 40 is half. Is 10 over 40 is half. It's 1 of 20 is half. So that brings us to a very, very important term called the homogeneity coefficient. Homogeneity coefficient. Homogeneity coefficient. It is simply the first HVL, the first HVL over first HVL over second HVL. For a polyenergetic beam, which we use, the first HVL, this number 1 over 2 is for monogenetic beam, it is always equal to 1. It is always equal to 1. The first HVL and the second HVL, the value will always give us 1. And if you know the value of the HVL, that's a 2 millimeter of aluminum. You place 2 millimeter of aluminum here. And again, after that, some photons have been transmitted. You place another HVL, another HVL. At the end of the day, we are going to have 1 as the homogeneity coefficient. But for polyenergetic beam, this value is not 1. It is a range from let's say 0.5 to around 0.5. So the hertz, in fact, for polyenergetic beam, the second HVL is always greater than the first HVL. Of course, it's a common question. The second HVL is always greater than the first HVL. That is to reduce the amount of thickness of this thing by 1/2. You have to increase the second HVL. But for monogenetic beam, you don't need that. You don't need that. And we have around 12 more minutes. Do you have anything? Or can we continue? In fact, we have to finish this video. This is 8:40.
On your mic.
Is that what?
Well done, sir.
Hello.
Good morning, sir.
Yeah, good morning.
This is Dr. Ashola on the line. So I want to know, please, can you expatiate further on the homogeneity coefficient? Because I didn't really understand.
Okay. Homogeneity coefficient. Okay, let me take it this way. You have, let's say for 140 keV gamma ray for a monoenergetic beam. We don't encounter it in diagnostic radiology except in nuclear medicine. For example, in the use of technetium 99M in the imaging. This is the energy of the gamma ray that results from the the decay of technetium 99M to technetium 99, 140 keV, the photon that will be given up. So if you have that photon, and you bring in an attenuator at this energy, you know the attenuator, the amount of thickness of any material is there, millimeter of aluminum, millimeter of blah, blah, blah. Let's say we're looking at it. Let's say we have seen it to be 1.5 millimeter of aluminum. You bring it. It's going to reduce the intensity by 1/2, assuming the dose rate. The intensity can be measured in terms of anything. It can be measured in terms of the absorbed dose, or the exposure, the absorbed dose, the dose rate, and so on and so forth. All these those descriptors can be used to characterize the energy. They characterize the behavior. So at the end of the day, you have maybe 40 what was it, microgray per millimeter, microgray per hour. So if we know the HVL, it's expected that this will give us if we measure with a meter here, you have 50 microgray per hour. That will be the dose rate. If you not take another, because some photons will come out, you not take another 1.5 millimeter of mercury, of aluminum, 1.5 millimeter, and you place it here. This one will reduce it by exactly 1/2, 20, 10. So the homogeneity coefficient is this HBr, which is a 1.5, because 1.5 millimeter, we actually reduce it again by 1/2. So 1.5 over 1.5 will give us 1. This is the first HBr. This is the second HBr. It's going to exactly give us a HC, the homogeneity coefficient of 1. But this is not the case for polyenergetic beam. For polyenergetic beam, because the energy will increase. For polyenergetic beam, of course, we don't want to use this, because as told us before, you can use so many dose descriptors. By using this and those descriptors of dose rate to explain this HVL, I can as well use a number of photons transmitted or whatever. So for polyenergetic beam now, for polyenergetic beam, it has so many energies. If we do that for polyenergetic beam, we use another 1.5 millimeter of aluminum. Let's say we use 1.5 millimeter of aluminum. We are not going to get okay, we use 20. We get a particular amount here, which of course might be 20 or might not. Let's say we got 30 microgray per hour. If we use this 1.5 millimeter of, we are not going to get, sorry, this. Okay, let's still use 20. If we use it by half, which we have, of course, it might not be 1.5, a particular value, but let's just stick to this 1.5. If you now use this 1.5 millimeter of aluminum, you are not going to get 10 here. It's not possible. You are not going to get 10 because this energy is this X-ray or this gamma ray is a polyenergetic. The effective energy of the beam is what we can actually calculate because it has so many bands of energy. We have we might have some 80 kV here, some 90, 60, and so on and so forth. It's a range of energy. So this 1.5 millimeter is not going to reduce it by 1/2. What will reduce it by 1/2 is an amount of thickness that will be greater than 1.5. Let's say it has been calculated, it has been measured. You might see that 2.3 millimeter of aluminum will be required to reduce this to 10 microgray per hour. You can see. So 1.5 over 2.3, 1.5 over 2.3 is not going to give us 1. It will have a number less than 1. Typically, in a diagnostic energy range, the homogeneity coefficient is around 0.5 to around 0.7. So at the mammography, you can have a very, very quality HC of around 0.9. I don't know if I have made sense.
Thank you very much, sir. Understood, sir.
Okay. I think So the remaining things are just radiation units and measurement, which you can actually read up. Exposure, absorb dose, equivalent dose, and effective dose. Those ones are not so much of a problem. You can actually read those ones up. Radiation units and their measurement. Radiation units and their measurement. Their measurement. So do we have any other questions today? We have to, we use the next month, Wednesday for the quiz. We use it for the quiz and discussion, correction of the quiz. Do you have any questions? Or can we continue? Do you have a class? I mean, duty post.
Hello, sir. Good morning, sir.
Yeah, good morning.
Yes, I think we can stop here. Work starts by 9 now.
Okay. I knew, I just wanted to ask. Maybe today
Thank you,
might
sir.
be a different day. Okay. So then just be expecting the quiz and the quiz to your inboxes as from today. Thank you very much for the class, for coming on board. We'll see you on Wednesday.
Thank you very much, sir. We are very grateful.
You're welcome.
God bless you.
Bless us all.